All right, so as I mentioned, permutations and particularly combinations, this provides us a nice bridge from what we have been talking about, independent, dependent events, into what we will be talking about. This is not covered in our textbook because it's based off of the presumption that you have already learned this. And just from working with students previously, and I asked my first class this, not everybody has seen this. Okay? Some of you, okay, you may have talked about this in FST. That's great. Okay? Hopefully this is just a little bit of a refresher. But if this is brand new for you, that's fine too. Okay? We're going to connect this to what we've already talked about, hopefully make sense out of this. So this is all based off of this counting principle that we're going to see in just a second again, and then be able to calculate these permutations and combinations. I will be showing you the equations for them. I don't really care about you using the equations. We have the calculator. I'll show you how to do that with the calculator coming up as well. Okay, that's what's helpful. West Virginia Mountaineers. These were their college football uniforms in the 2018 season. It seems like college football teams, they change their uniforms or have different options available every season. So I haven't updated it in a couple of years, but in 2018, these were the options that they had available to them. They had 4 different helmets. They had blue, gold, white, and then this throwback logo on their white helmet. 3 different jerseys, blue, white, gold, and then 3 different pants. So we had seen problems like this a couple weeks ago. How many different uniform combinations were possible? Well, one possibility, if you really wanted to, you could map out every single possible combination. Okay? Pick a helmet, okay? Branches out 3 different ways to the jersey. Okay? Blue helmet, blue jersey, blue helmet, white jersey, blue helmet, gold jersey. And then it branches out again, 3 more ways to the pants. Blue helmet, white jersey, blue pants, blue helmet, blue jersey, white pants, and so forth. Okay, it's a mess. I already expressed my displeasure with making tree diagrams a few weeks ago. Okay? The important thing, the shortcut for the counting principle, is you're multiplying your possibilities together. We have 4 different helmet options, 3 different jersey options, 3 different pant options. 4 times 3 is 12. 12 times 3, 36 different uniform possibilities for their football team. Okay? Now, these events were independent of each other. Okay? By selecting one, that didn't impact the number of options that we had for other selections. And we've talked about independence to a great extent. We have a verbal definition. Okay? Making one selection does not impact other selections. We also have a mathematical definition, an equation. We can multiply individual possibilities or probabilities, and their product will equal the probability of both of them happening simultaneously. Okay? This counting principle is the foundation for this equation. So a couple examples here. You're going to notice that I am not going to do most of these example problems today. Okay? I'm skimming over a lot of these because we already know what they contain. Okay? In fact, I think we already did like these marble problems together. So let's say, do this one here. 10 cards are numbered from 1 to 10. They're placed in a box. 1 card is selected randomly and then replaced. That is important. Another card is selected at random. What is the probability of selecting a multiple of 3 and then a multiple of 2? Well, 10 cards for our first selection. We want a multiple of 3. So that would be 3, 6, or 9 in this range of numbers. So 3 possibilities out of those 10 cards. Now, it is important that once we make that first selection, it is then replaced. Because that second selection, we're still picking from 10 cards, and there we want a multiple of 2. If we had selected a 6 for our first card, it was a multiple of 3. But that's also a multiple of 2. So if there's no replacement here, then these are definitely dependent upon each other. Okay? Because of the overlap in the selection, but also because of the totals that are changing. But because we are replacing it and, we'll say shuffling, and randomly selecting, we have multiples of 2, 2, 4, 6, 8, 10, and 5 different options available to us for our second one. We know we can multiply these together. 3 times 5 is 15. 10 squared is 100, so 15 out of 100, 15%, 0.15. Again, nothing new there, just kind of analyzing step by step. Now, dependent events. Okay, if we had not replaced those cards, then those probabilities are dependent upon each other. And this is where we got down that branch of probability that was looking at conditional probability. Okay? Here's a variation of that wording here. Probability of A and B equals the probability of A times the probability of B after A. Or in other words, probability of B given that A has occurred. Okay? Now, we're not getting that complicated right here, but that's what this is. And we have a class of 18 boys, 12 girls, so 30 total students. 2 students are chosen at random. What is the probability that the students chosen will be a boy and a girl? Well, the order doesn't really matter. We have 18 boys, so let's just go with that first, the way that it was presented. We're selecting 18 out of the 30 students. Our second selection should be a girl then, 12 girls, but now we only have 29 students left after we've made that first selection. So because of that changing total, these are dependent events. 18 out of 30 times 12 out of 29. Here's our probability. There's about a 24.8% chance of that happening. The same thing doesn't change if we're looking at multiple boys or multiple girls here. If we wanted the probability of selecting 2 boys, 18 out of 30 for that first selection, but now there are only 17 boys remaining, and again, 29 total students in the class for that next selection. And changing probabilities as we go down the line. So let's just do one of these here. 10 cards are numbered from 1 to 10, placed in a box. What is the probability of selecting 1 even card, setting it aside, and then selecting 1 odd card? Well, we're looking at probability of selecting an even card. So we have 5 even cards out of 10. 2, 4, 6, 8, 10. We set it aside, and then we want to select an odd card. Now we will have all 5 odd cards, 1, 3, 5, 7, 9, but only 9 overall cards remaining. These would be dependent on each other. Multiply them together. 5 times 5 is 25. Out of 90, so we're looking at slightly more than 25% if we were to divide this out. 25 divided by 90 is, 20.27 repeating, or about 28%. Anybody have any questions so far? Good. Now, notice how I've kind of gone seamlessly between number of possibilities and probabilities. And they're basically interchangeable in terms of that counting principle. If you're looking at uniform combinations like we did, helmets times jerseys times pants, or first probability times second probability, it's the same idea. So we use this for probabilities, but a lot of times when we're looking at total number of possibilities, which is what a permutation and combination does, okay, we're just looking at the numbers themselves, not this ratio that is a probability. So with that in mind, let's look at this license plate problem. Now, a standard issue Pennsylvania license plate looks like this, where we have 3 letters, the little keystone symbol, followed by 4 numbers. Now, this is ignoring personalized plates, vanity plates, those sorts of things. Okay, this would just be if you don't care and you're letting them assign you a license plate, this is the format that it takes. Now, we want to determine how many license plates can be issued in this format. Well, this is kind of like that uniform problem, where let's look at the number of possibilities that we have for each slot. Okay? These are letters, these are numbers. So we have this format, letter, 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 number, 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 number. For this first letter, how many different options do we have? The first character, I should say. What is it? No, for this one. It could be A, it could be B, it could be C. 26, yeah. We have 26 different letter options. Now, we can repeat. It doesn't matter. We could have AAA as our letters on our license plate. So for our second slot, 26 options again. Third slot, 26 options again. And these will be multiplied together. For the numbers, how many possibilities do we have for this first digit? Plus 0, so 10. Yeah, so 1 through 9 and the 0, so 10 options here. Again, we can repeat. This could be 1, 1, 1, 1. So 10 for each of these. Multiplying them all together, multiply the 2 together. Or if we wanted to shortcut this algebraically, we have repeated multiplication. This is 26 to the 3rd power times 10 to the 4th power. And if we multiply this out, 26 cubed times 10 to the 4th, we get a pretty big number. 175,760,000. 175,760,000 different possible license plates could be issued in this format. So that's a pretty big number. I mean, I'm not sure what the population of Pennsylvania is, but again, you're not talking about each person, you're just talking about number of license plates, number of registered Pennsylvania vehicles like that. So they do have some options. Now, some of you might recognize that no, they're not going to issue every single one of these license plates. Like there might be some 3-letter word arrangements that you don't want on a license plate, right? Okay, maybe I'm talking to the wrong crowd. Teenage boy, you might like an ASS license plate, but I don't think that the general Pennsylvania resident wants that on their vehicle. So they don't issue those, they don't issue some other ones, but you still have a large base to pull from here. Okay? Now, just theoretically here, what if you could not reuse digits? Let's look at how that changes this calculation. Okay, so we still have 26 possibilities for that first character. But then let's say that that first letter is an A. Now we're saying we cannot reuse it, so that leaves us with 25 letters, B through Z, for our next selection. And then after that, we've already used A, we've already used B. Okay? C through Z, we have 24 options. And same kind of thing for the numbers. 10 for that first digit, but then 9, then 8, then 7. And if we're to multiply these out, clearly we're going to have a smaller number of possibilities. 26 times 25 times 24 times 10 times 9 times 8 times 7. We're looking at 78,624,000. So less than half of the number of possibilities if we had these exclusions. Okay? Still a lot, but really not as many, not nearly as many, when you're not allowed to repeat or reuse digits. Now, we shortcutted the notation up here. Oops. We were able to use the exponents to help us and really helps kind of visualize what's going on. Okay? Number of possibilities raised to the number of those trials. Okay? We could do the same kind of thing if we're looking at coin flips, if we're looking at like a multiple choice test. Okay, what's the probability of guessing? If we have a 10-question multiple choice test where we have A, B, C, D as our options, and 4 options on each one, 4 options for the first problem, second problem, third problem, all the way up through all 10 problems, 4 to the 10th power, that's the number of possible tests that we have. Only one of those is the perfect arrangement of correct answers, so that probability would be 1 over 4 to the 10th. Okay? So these exponents can help us when we have this independence like that. Okay? When they're dependent like this, we don't have a shortcut way to write this, at least in terms of exponents. But that's when the permutations and combinations come into play. So let's talk a little bit about these. Now, my guess is that if you do have some background with permutations and combinations, if you remember anything, this is what you remember about that. A permutation is an arrangement in which the order matters. A combination is an arrangement in which the order does not matter. Permutation, order matters. Combination does not matter. That's a good rule of thumb about 75% of the time, I would say. It's not a perfect understanding of the differences between these two. And as we see some example problems, I'm going to clarify what I mean by that. Okay? But if you really want to simplify things, yeah, that's an okay way of remembering it. Okay? Now, let's give an example of the differences here. Let's say pizza place offers only 3 toppings of pizza. I don't know, probably not good for business offering that limited number of choices, but olives, pepperoni, mushrooms. How many 2-topping pizzas can Jack order? Well, it doesn't matter on the pizza if you have pepperoni and mushrooms or mushrooms and pepperoni. This is a case where the order does not matter. This is a combination. Now, this one, Rosario has 5 awards. How many ways can she display 3 of them on her wall? Well, the order does matter here. Okay, let's say that she's running races and she has some like first place, some second place, some third place awards. There are differences between these. She doesn't want to put a wall that contains 3 third place trophies on it when she has first place trophies that she could display. So the ordering of them does matter. There's a difference between a first place, a second place, a third place versus third place, third place, third place. This would be a permutation because that ordering does matter. Now, here is the equation for a permutation. Okay? We use this NPR, National Public Radio, NPR, where N is the number of choices that you have, R is the number of selections that you're making. So for a permutation and a combination, N is always greater than or equal to R. Okay? N is always the bigger number. Okay? If they're the same, then they're the same. Now, I said that you don't have to worry about the equation, but we've seen this a couple times already this year. It's important for us to at least look at what's happening with the equation. We use this exclamation point, which in math is called a factorial symbol. What a factorial symbol does is it multiplies every integer all the way down to 1. So if you had 4 factorial, this is 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is still 24. Now, when you're working something like this, let me talk about how the calculator works for this right now. Before the end of class, I'll flip screens and show it to you. But if I wanted to do this 4 factorial on my calculator, I press the 4, I go to math, and then all the way over to the probability column, you'll see number 4, the exclamation point, the factorial symbol. But more importantly, above that, you have NPR and NCR for permutation and combination. Okay? But you could select the 4 factorial. There's the 24. Again, I'll pull this up on the screen in a few minutes. It's just, a lot of work to go back and forth. I'm fine with you using the calculator. This award problem, we said it was a permutation. So this would be a permutation of 5 and 3. She has 5 things to choose from. She's picking 3 of them. You would enter it like this: permutation of 5 and 3, where 5 would be the first number that you enter. Go in math probability, select permutation, and then type a 3. If you were using the equation, we see it's n factorial divided by the quantity n minus r factorial. So we have the bigger number on top. They're subtracting the difference in the denominator and then take that factorial. You can see how, working this out, you're going to get some cancellation down here. In this case, it's just the 2 factorial, 2 and the 1. So what's happening is you're just multiplying 5 times 4 times 3. Think about this with respect to what we just did. 26 times 25 times 24, and then we stopped. For the numbers, 10 times 9 times 8 times 7, and then we stopped. These were actually permutations, where for these 3 letters, you had 26 letters to choose from. You had 26 letters to choose from. We wanted 3 of them. In this case, the ordered mattered, so that was a permutation. Okay. So we had 26, 25, and then 24. For the numbers, we have 10 digits, 0 through 9. We're selecting 4 of them. The order matters. It would be another permutation. We could have thought of this as a permutation of 26 and 3 times a permutation of 10 and 4. That would have gotten it the same 78 million. I will say that it's not an issue with the newer calculators, but some of the older calculators, if you were to do a large permutation, sometimes it would give you an error message that it could not be done. For example, let's say we had a permutation of 103. So 100 different options. We only want 3 of them, but the order does matter. Well, the way the calculator does this is it starts to do 100 factorial divided by 100 minus 3, so 97 factorial. Well, if you were to type in 100 factorial on your calculator, it's doing 100 times 99 times 98 times 97, all the way down to 1. It gives you an error message of an overflow. That's too big for the calculator to do, even in scientific notation. So, when it's trying to calculate that, and it finds it can't do 100 factorial, it stops. It says, I can't do it. Like you guys on homework problems, right? You read over it. Oh, this looks too hard. I can't do it. Move on to the next one. Question mark. All right? Well, it actually could be done. Because think about this cancellation that we see right here. Okay? Once we get to 97 factorial, that's going to divide out with everything in the denominator. The 97s, the 96s, 95s, all the way down to 1. So really what's left is 100 times 99 times 98. The 97s and all the way down are going to divide out. So 100 times 99 times 98 gives us 970,200. Not that big of a number. So just something to be aware about. If you're going into like computer programming, you're going to see permutations and combinations, some like logistics and supply chain sorts of fields. They use permutations and combinations quite a bit as well. Okay. All right. Our first 2 example problems is just tell whether the situation involves a permutation or combination. How many different ways can 20 students line up for an assembly? Talking elementary school here. Okay. Would that be a permutation or combination? Come on. You remember back in elementary school, like it was a big deal to be first in line, whether you're going to an assembly or a lunch or something. Okay, that's a permutation. Okay, the order does matter. Okay, having student A, then B, then C, that's different than student C, then student N, then student H. Okay, this is a permutation here. In fact, it's a permutation of 20 students and you're selecting all 20. Okay, in other words, 20 factorial. Okay, 20 options for that first student. You've assigned that student, and then you have 19 options for your next student. And then 18, and then 17, all the way down. Number 2, how many ways can a teacher choose 2 students from her class of 15 to distribute flyers to other classrooms? Well, those 2 students that are selected, it doesn't matter if it's student A and student B, or student B and student A. That group of 2 is performing the same task. The order does not matter. This is a combination. This is where I get into that idea that maybe that phrasing of order matters or order doesn't matter isn't the best way to go. I prefer to think of it as the task or the job that each person is doing. Is it different or is it the same? Okay? Order or no order? In this case, the 2 students, they're doing the same task. Okay? Doesn't matter which is which. So it would be a combination. We are told that these following problems are all permutations. Here's an example right here. A 2-digit letter code is used to access a program. How many codes are possible if the same letter cannot be used twice? All right, well, a 2-digit code isn't exactly like cracking into Fort Knox here, but the same letter cannot be used twice, so you have 26 options for that first one and 25 options for that second one. Multiply them together, or you could think of this as a permutation. Of those 26 options, you're choosing 2. You cannot reuse them. Okay? So 26 times 25, 650 possibilities. Somebody would be able to crack that code eventually. Any questions so far? Now, with the combination, and again, I will say that moving forward, like we are focusing on combinations for our next lesson, binomial distributions. This is what we'll be using. The order does not matter. So the equation just has a slight variation to it. We have this extra r factorial multiplied in the denominator. That's the only difference in the calculation. But because we have that there, we have a larger value in the denominator that is making us divide by a bigger number, which is reducing the total number of possibilities. That makes sense because we're looking at A and B is the same as B and A. In a combination, those are the same. In a permutation, they're counted as different outcomes. So here's that pizza problem. Now they're offering 10 different toppings. Abel wants a pizza with 4 toppings. How many different 4-topping pizzas can he choose from? You can see how we have the n greater than or equal to r still. Okay, so 10 is the n value, 4 is the r value. We do have that difference. 10 minus 4 is 6 factorial, but we also have a 4 factorial here because it's a combination. Be careful with the order of operations. If you were to reduce this by hand, you can still reduce it. The 10 factorial and the 6 factorial, okay, all those 6's and down can divide out, but you still have 10 times 9 times 8 times 7 in the numerator, and you still have the 4 factorial left alone. Okay, a factorial is multiplication. Okay, so think about how that fits into the order of operations. 5,040 divided by 24, we have 210 different choices. Okay? Or you just type in on your calculator 10 combination 4 and get the same answer. Again, I will show you how to do that momentarily. Let's take a look at number 7. A school is offering free dance tickets to 4 people from a class of 18. How many groups of 4 can be chosen? Well, if you're selected, you're part of this 4-person group. The order of that group does not matter. You're included in the group. So this is a combination of 18 and 4. An English exam consists of 7 possible questions. Students must choose to answer 3. So it's like essay prompts. Okay, 7 different prompts. You're only picking 3 to write about. And it doesn't matter if you pick A, B, and C, or if you like C first, and then you choose B, and then you choose A. You're still answering the 3 questions. It's a combination because the order doesn't matter. Combination of 7 and 3. From a group of 15 volunteers, 8 will be chosen for cleanup duty. How many groups of 8 are possible? They're all performing the same task, so it's a combination of 15 and 8. Now, I will say that a common type of problem here is selecting people to serve different roles. Like, let's say we had 15 student council members, and of those 15, we need to identify a president, a vice president, write this out, president, vice president, secretary, and treasurer. Each of these performs its own distinct roles. So 15 people to choose from, selecting those 4 roles, would that be a permutation or a combination? Permutation. Because the order does matter, they're serving different roles, as opposed to like what we saw in 7, where we're just picking 4 people to go to this dance as a group. Okay? That's what I mean, where sometimes thinking of it as, does order matter or order not matter? It's not the best approach. Think of it as, does the role differ from selection to selection? Okay? You have these 15 people, you're probably going to select a president first. And then once that president's been identified, you have 14 people remaining to appoint a vice president. And then you have 13 people left to pick a secretary, and then 12 to pick a treasurer. Okay? So that would be a permutation. If I had changed this so that of these 15 student council members, 4 people were going to sit in on the next school board meeting, and well, they're all doing the same task. They're just sitting in on this meeting. It's a 4-person committee. That would be a combination. Okay, because the role is all the same. Okay, so think about that in terms of what service are they performing. So these last 3 questions here, do they involve permutations or combination? A stationary catalog offers poster board in 5 different colors. Deontay must choose 2 colors for his history project. How many orders of 2 poster boards of different color are possible? Would this be a permutation or a combination? Combination. Picking red and blue is the same as picking blue and red. Doesn't matter. So this would be a combination of 5 and 2. How many ways can 4 people arrange themselves around a table with 12 seats? Permutation or combination? Okay. We're talking about how many ways that you're seated around the table. Okay. Individuals and ordering does matter here in terms of like this person versus this person. This would be a permutation of 12 and 4. Then our last one here. An ad for a grocery store states that when 6 cans of soup are purchased, $2 will be donated to a local charity. The store carries 11 flavors of soup. How many ways can 6 cans be chosen if each can is a different flavor? All right. First thing, this is a meaningless number in the problem. We don't, well, I shouldn't say we don't care about the $2 donation to charity, but it's not relevant to our problem here. We're buying 6 cans, 11 flavors to choose from. We need different flavors for each selection. It doesn't matter if in my selection of 6 soups, I have tomato soup, vegetable soup, beef stew, or beef stew, vegetable soup, tomato soup. Okay. They're part of my group of 6. So this is a combination, 11 and 6. Any questions? I did say that I wanted to show the calculator, so let me flip screens. If you haven't figured it out, already. It's pretty straightforward. Okay, so your options here are under the math and then that far column probability. You see numbers 2, 3, and 4, permutation, combination, and the factorial. Now, when you're entering a permutation or combination, you do need to put the n value first. Okay, so when we're talking about like 15 student council members and president, vice president, secretary, treasurer, that was a permutation. So math probability number 2 for a permutation, selecting 4. Okay, so number, selection, and then number. Hit enter. 32,760 different possibilities. To show you that calculator error, if I were to try to do 100 factorial, there's that overflow error. Okay? But most of the newer calculators have fixed it. If I try to do 100 permutation, select 3, okay, yes, it will do that now because it recognizes that 97 factorial all the way down is going to divide out. So 100 times 99 times 98. Your homework. Flip the screens back. Okay, so your homework is 2 pages, pretty straightforward. Okay, some of these problems just reducing, a couple of ones like we had just talked about. Again, I don't care, you're fine just typing this in on your calculator. Permutation of 8 and 3. I don't need you to do it by hand. The second page of this, I will say several of these problems are more like the license plate problem, where you're multiplying out number of possibilities. Don't try to force a permutation or combination. Okay? Sometimes you can look at it like that, but like number 2 on the second page, you're looking at a VIN number, vehicle identification number, and it tells you how many possibilities you have with each character. Okay, so like we did on that license plate problem, lay it all out, look at how many possibilities you have in each slot, and then multiply them all together. Okay, yes, you will get a big number on that problem. Okay. Some of these you can look at as a permutation or combination. Others you may just want to look at using that counting principle. How many options do I have for the first selection? How many options do I have for the second selection? Third selection. Multiply them together. Okay? So, pretty straightforward. Submit this by Wednesday morning. And we have 20 minutes right now that you can start cracking on this. All right? Anybody have any questions at the moment? Okay. So, I do want you to remain logged in at home, but please make sure you're working. I will be here if you have questions. Okay? Be productive.